We begin with a reminder that pH measures a component of water. It is not the component itself. Like the number on a scale that measures weight, pH is a number on a meter that indicates the concentration of hydronium ions in water, in pH units. But why use pH at all for measuring hydronium ion concentrations, instead of just staying with moles per liter? After all, a hydronium ion probe generates a voltage that a pH meter then translates to pH units. It could just as easily translate the voltage to molar concentrations. The problem with doing that is the enormous range of hydronium ion concentrations normally encountered in municipal and environmental waters. This figure shows that the hydronium ion concentration can range from greater than 1 mole per liter in solutions of strong acids to 10 to the minus 7 moles per liter in pure water to less than 10 to the minus 14 moles per liter in solutions of strong bases. This is a range of more than 14 orders of magnitude. The standard way to measure and plot a variable that spans such a large range is to use a logarithmic scaling factor. Making pH a logarithmic scaling factor for hydronium ion concentration means setting pH equal to the logarithm of the hydronium ion concentration, as in this equation, which rearranges to this more useful form. As an example, if the hydronium ion concentration equaled 10 to the minus 3 moles per liter, then pH would equal minus 3, the exponent of 10. In the early 1900s, when the pH scale was first proposed, chemists saw the minus sign in pH as a problem. Measured values for hydronium ion concentrations are very seldom greater than 1, which causes the pH to almost always be negative. Although pH is just a scaling factor, chemists also wanted it to represent the hydronium ion concentration. Since a concentration can never be negative, chemists simply redefine pH as minus the log of the hydronium ion concentration by adding a minus sign here. This had the desired effect of making pH be almost always measured as a positive value. To show how this works, if we add a pH scale just above the hydronium ion concentration scale, we see that the pH is the same as the exponential power of 10, but without the minus sign. Adding the minus sign has the unfortunate side effect of making low pH values mean high acidity, and high pH values mean low acidity. This might seem counterintuitive until you remember that 10 to the minus 3 is a bigger number than 10 to the minus 4, so pH 3 is more acid than pH 4. In practice, pH is much easier to use than hydronium ion concentrations. The pH scale compresses the 14 orders of magnitude of the hydrogen ion concentration range into a more manageable 0 to 14 linear pH scale. And keep in mind that pH values are not limited to a 0 to 14 range. pH 0 to 14 is almost always sufficient for measurement of environmental and laboratory solutions, but this range is determined by technical and chemical limitations. At the pH equal 14 end of the scale, where water is very basic and hydronium ion concentration is very low, around 10 to the minus 14 moles per liter, the range is limited by the sensitivity of existing pH instrumentation. At the pH equals 0 end of the scale, where water is very acidic and hydronium ion concentration is around 1 mole per liter, the range is limited by water chemistry. which makes it increasingly difficult to support higher concentrations of hydronium ion. Although it's very rare to find water more acidic than pH equals 0, it can happen, and negative pH values have been reported. The most acidic water I have seen referenced is from an abandoned copper and zinc mine on Iron Mountain in California, now a Superfund site. Samples collected there in the 1990s had pH equal minus 3.6, a hydronium ion concentration of 10 to the 3.6 moles per liter, about 4,000 moles per liter. Next, why is it important to know that pH meters measure hydronium ions, not hydrogen ions? In pure water, H3O plus is made in the reaction of two colliding water molecules when one transfers a hydrogen ion to the other. Hydronium ion can also be made when an acid like hydrochloric acid, HCl, is added to water and contributes a hydrogen ion to a water molecule. The main point here is that water must be present in order to make hydronium ion. No water, no hydronium ion. No hydronium ion, no pH. Because water is needed for the measurement of pH. Any substance that does not contain any water, like a pure oil for example, cannot have a pH. And for substances like soils, which may contain some water, but water is not the main interest, when we measure soil pH, we really are measuring the pH of water that is contained in the soil. Dry soil has no pH. The hydronium ion is a pretty reactive species. It tends to transfer its proton to any other water molecule it collides with. It doesn't matter which water molecule the hydrogen ion sits on, but if the water contains other species, they can receive the hydrogen ion, and that can change the properties of the new molecule with its added proton dramatically. To illustrate how pH can influence the behavior of pollutants in water, consider two common pollutants. First ammonia and then phosphorus. Ammonia is a common surface water and groundwater pollutant. The neutral unionized form of ammonia, NH3, is very toxic, especially to aquatic life. The ionized form, NH4+, is much less toxic, but it serves as a nutrient that promotes algae blooms. Algae blooms can rapidly lead to depletion of dissolved oxygen through biodegradation of decaying algae. The distribution in water between unionized and ionized forms depends very strongly on pH. This plot shows how pH affects the way ammonia changes between its unionized and ionized forms in water. At pH 9.25, ammonia is divided 50-50 between ionized and unionized forms. When pH is less than 9.25, the less toxic ionized form predominates. And when pH is greater than 9.25, the more toxic unionized form predominates. Most natural waters maintain pH between 6.5 and 8.5, where the less toxic form, NH4+, comprises over 90% of total ammonia. But notice how rapidly the fraction of the more toxic form, NH3, increases from about 15% to over 80% when pH increases only 1.5 units, from 8.5 to 10. A short spike in pH to 9 or 10, as could happen when an algae bloom forms or a sudden downpour causes higher agricultural runoff, can result in a significant fish kill. Phosphorus is another common contaminant in natural waters that is strongly affected by pH. Like nitrogen, phosphorus is an essential nutrient for most life forms, aquatic and terrestrial. But unlike nitrogen, most phosphorus comes from low solubility minerals, phosphates, and the portion that does dissolve sorbs strongly to mineral and organic soils. This plot will show how small changes in pH can quickly increase the ratio of dissolved to sediment-sorbed phosphorus. Phosphorus is most strongly sorbed to sediments between pH 5.3 and 8. In this pH range, about 95% of phosphorus in unpolluted lakes and streams is sorbed or precipitated in sediments, and the dissolved and biologically available concentrations are very low, seldom above 0.1 milligrams per liter. This normally is sufficient for most aquatic life, but pH strongly affects the strength of phosphorus sorption to sediments, and slightly higher dissolved phosphorus concentrations can quickly cause algae blooms. When sediments are a significant reservoir of phosphorus, any change in pH, either more acidic or more basic, can change the water from being supportive for aquatic life to being hazardous. Values below 5.3 or higher than 8 cause phosphorus to desorb from sediments and become dissolved and biologically available. Note how a small change in pH, either plus or minus, can increase the percent of phosphorus that is dissolved from around 20% to over 60%. With phosphorus, any small change in pH out of the 5.3 to 8 range can make a beautiful clear water eutrophic. Now, how is pH related to the acidity and basicity of water? We've learned that pH less than 7 indicates acid water, pH greater than 7 indicates basic water, and pH equals 7 is neutral water. Those guidelines are pretty good, but they are not the whole story. For example, why is pH equals 7 the special value of acid-base neutrality? For this, we have to look closer at the acid-base properties of water. In pure water, the only source of hydronium ion is the reaction shown here. But pure water is always acid-base neutral even though it contains hydronium ion at a concentration of 10 to the minus 7 moles per liter. In pure water, something must cancel the acid nature of hydronium ion for water to be neutral. That something, of course, is hydroxyl ion. Note that when two water molecules react to form ions, hydronium ion and hydroxyl ion are always produced in equal amounts, one molecule of each. This means that in pure water, which is always neutral and has no other source of ions, the hydronium ion and hydroxyl ion concentrations must always be equal. The reason pure water is neutral is because the concentrations of hydronium ion and hydroxyl ion are equal. This applies to all water, pure or not. H3O plus is the chemical species that causes the property of water we call acidity. OH minus is the chemical species that causes the property of water we call basicity. When water contains equal concentrations of H3O plus and OH minus, acidity and basicity cancel, and water has the special property of acid-base neutrality. Pure water is always neutral, because its concentrations of hydronium ion and hydroxyl ion are always equal, and their ratio equals 1. Water is acidic when hydronium ion concentration is greater than hydroxyl ion concentration, and their ratio is greater than 1. Water is basic when hydronium ion concentration is less than hydroxyl ion concentration, and their ratio is less than 1. In all water, pure or not, acidity is determined by the ratio of hydronium ion concentration to hydroxyl ion concentration, not by the hydronium ion concentration alone. But why are hydronium and hydroxyl ion concentrations equal at pH 7 to make water be neutral at pH 7? The reason that pH equals 7 is the special pH of water neutrality is related to the fact that the water ionization reaction is reversible. The most observable property of reversible reactions is that nothing seems to be happening. We take for granted that the pH remains constant during a measurement, even though the reaction above is constantly occurring and making more hydronium ions. In pure water, for example, the pH is always equal to 7, as if the reaction stopped producing more hydronium ion after reaching pH 7. This is characteristic of reversible reactions. In reversible reactions, like water forming hydronium and hydroxyl ions, the forward reaction never stops. Instead, the reverse reaction also takes place, where hydronium and hydroxyl ions recombine to form water molecules. In all reversible reactions, there is always a particular concentration of products where the reverse reaction rate exactly equals the forward reaction rate. When these opposing processes continue at equal rates, a state of dynamic equilibrium is reached, where the concentrations of reactants and products remain constant, and there is no net change in the overall composition of the system, even though individual molecules continue to react. It was shown experimentally that this condition of dynamic equilibrium is reached when the hydronium and hydroxyl ion concentrations fit the equation hydronium ion concentration times hydroxyl ion concentration equals 10 to the minus 14 moles squared per liter squared. The same equation in pH units is pH plus pOH equals 14. Like pH for hydronium ion, pOH is a logarithmic scaling factor for hydroxyl ion. It's these equations that make water be neutral at pH 7. Using pH terms, this equation is a required condition for the reversible water ionization reaction to be in dynamic equilibrium. And this equation is the required condition for water to be acid-base neutral. The only pH value that fits both the equilibrium condition and the neutrality condition simultaneously is pH equals 7. For equilibrium, if pH equals 7, pOH must also be 7 to make their sum equal 14. And when pH and pOH are both equal to 7, the condition for water neutrality is also met, because the ratio pH over pOH equals 1. But if pH does not equal 7, the condition for equilibrium can still be met. The pOH just changes so that pH plus pOH still equals 14. But there's no way for the neutrality condition to be met. For example, if pH equals 3, the pOH will be 11 to maintain equilibrium. But then the ratio pH over pOH is 3 over 11, which is less than 1, and the system is acidic. Only pH equals 7 can make the pH-pOH ratio equal to 1. This ends the chemistry lesson. We've learned that pH is a convenient scaling factor for hydronium ion, that substances that contain no water have no pH, that water acidity depends on the ratio of hydronium ion to the hydroxyl ion, that pH equals 7 is the only possible pH for water neutrality, and that pH can strongly influence the behavior of water pollutants. The good news is that, with the exception of this last item, you don't need to know any of this to use pH. This cartoon from the New Yorker shows a similar case.